Problem 516. Two long coaxial solenoids each carry current I, but in opposite directions. The inner solenoid has a radius A with N1 turns per unit length, and the outer solenoid has a radius B with N2 turns per unit length. Find the magnetic field in each region. Inside the inner solenoid, between the inner and the outer solenoid, and outside both solenoids. So in order to do this, we have to know the formula for a solenoid, and we can also use the superposition principle, and we can also use the right-hand rule to use this superposition principle, because we want to know the directions of the magnetic fields. So the right-hand rule says that for solenoids, we wrap our right hand around the direction of the current. So for our outside coil, we can see that the arrow is pointing down. So our fingers are going to be wrapping around in the down direction, this direction. So it's wrapping this way, and our thumb points to the right. So that's our direction of the magnetic field for our outside solenoid. For our inside solenoid, now the current is pointing up, so we wrap our fingers into the page, and our magnetic field points to the left. So again, for our outside solenoid, it's pointing out of the page, so our magnetic field is to the right. And for our inside solenoid, it points into the page, and our magnetic field is to the left. For the magnetic field of a solenoid, the magnetic field is mu naught times N times I. If we were to run a square Amperian loop through this, we would get BL is equal to mu naught N I times L on the inside. That's for when we apply Ampere's law. The magnetic field outside of a solenoid is equal to 0. Superposition principle says that if we have a magnetic field that has multiple sources, we can add up all of the individual sources, and it'll give us the total magnetic field B. And the reason why the outside magnetic field of a solenoid is equal to 0 is because we can draw amperes, like an Amperian loop, around the entire solenoid. This would enclose the current flowing in both directions. The net current, therefore, would be equal to 0, because we would have positive I plus negative I. And according to Ampere's law, if the net current is 0, the magnetic field must also be 0. Next, I decided to draw my solenoids like this. So we have the dots are going out of the page, and the crosses are going into the page. And I wrote it like this because I wanted to represent a solenoid, or two solenoids like this, so that I could apply Ampere's law. Taking a Amperian loop around the entire region, for B3, I'm going to label these regions 3, and this is 2, and this is 1, 2, and then 3. For B3.dl, closed loop integral is equal to mu naught N I enclosed. But as stated earlier, the current enclosed is equal to 0, so that means B3 is equal to 0. For region 2, the closed loop integral B.dl is equal to mu naught N I enclosed. So when I do my Amperian loop, I'm going to do it up here. current going this way now. And it's a square loop of side length L. So if this is infinitesimally dl, my b dot dl becomes bl because I'm integrating dl. BL is equal to mu naught N2 I L. Sorry, there's an L right here. Dividing out the L, you get B2 is equal to, I'll write a 2 right here, mu naught N2 I. And I'm going to define this direction as the z direction, so z hat. B2 is equal to mu naught N2 I. For our third inside the inside solenoid, we draw our Amperian loop, and now it covers the inside of 1 and it covers 2. So we already have this contribution. And if we want to find this contribution from B3, B1, we can we have to know that the current is going in the opposite direction, so our magnetic field is going to be pointing in the opposite direction. So B3.dl is equal to mu naught N I enclosed times L. Using and let's say it's a side length L, BL is equal to mu naught I. They both have I, they both have L. The only thing is now we have N2 minus N1 because they're going in opposite directions. So we can divide by the L. B is equal to mu naught I times N2 minus N1. And this is from the superposition principle. And that's in the z hat direction. Anyway, that's all. Thanks for watching.